So now let's look at this integral. We want to find the area of the region between the graphs of f of x equal to 2x squared plus 10, g of x equal to 4x plus 16, x equal to negative 2, and x equal to 5. And here's the graph that corresponds to that. And you can notice that there are 3 different regions here. And those are each going to correspond to different integrals. So this first one here we'll see runs from negative 2 to negative 1. And we see that the red function is on top. So I have 2x squared plus 10 minus the bottom function, which is 4x plus 16 dx. For this center part, this runs between negative 1 and 3. And this time we see the blue function is on top. So I have 4x plus 16 minus 2x squared plus 10 dx. And then finally, this last region, which runs from 3 to 5 and has the red function on top. So 2x squared plus 10 minus 4x plus 16 dx. So now let's actually calculate this. So we would want to add all 3 of those integrals together. So the first one ran from negative 2 to negative 1. And after we simplify it, it would be 2x squared minus 4x minus 6 dx. The next one ran from negative 1 to 3. And after simplified, it would be 4x plus 6 minus 2x squared. The last one ran from 3 to 5 and would be simplified to 2x squared minus 4x minus 6. So when we integrate this, I would get 2/3 x cubed minus 2x squared minus 6, taken between negative 2 and negative 1. I get 2x squared plus 6x minus 2/3 x cubed, going between negative 1 and 3. And then I get 2/3 x cubed minus 2x squared minus 6x between 3 and 5. And if you evaluate all of these and work that all out, you get 142 over 3. So if f and g are continuous functions, where the function is given in terms of y over the interval c to d, we can do the same thing. The area of the region bound by x equal to f of y and x equal to g of y on c to d is the integral from c to d of f of y minus g of y dy. So let's go back and look at our first example. As a reminder, our graph looks like this one. So this was the square root of x, and this one is x squared. We know that this is the point 0, 0, and this is the point 1, 1. So if I want to do this in terms of y, I'm now going to look at the y coordinates for my bounds, which in this case is still 0 and 1. For my functions, I'm going to look at left and right rather than top and bottom. On the right, I have y equal to x squared, which means that the square root of y is equal to x. So this one is the square root of y. The one on the left is y equal to the square root of x, squaring both sides. Y squared is equal to x, so minus y squared dy. So this gives 2/3 x to the 3 over 2 minus y to the 3 over 2 minus 1/3 y cubed, going between 0 and 1. And if we evaluate this, we will get 1/3 once again. Now let's go back and look at our second example. So in this case, our graphs look like this. We know that these intersected at the points -1 and 2. If I stick in -1 to either one of these equations, I get a y-coordinate of 2. If I stick in 2, I get a y-coordinate of 5. We also, in this case, need to know which function is left and which function is right, which can be kind of tricky. So we're going to break this into two pieces. Here's my dotted line. So we'll have the bottom region and the top region. The bottom region runs from this point, which is 1 in the y-coordinate, up to this point, which has a y-coordinate of 2. And this bottom region only deals with our first function, y equal to 1 plus x squared. We can subtract 1 and take a square root to get our function 4 in terms of y. So this is the square root of y minus 1 dy. We then want to move from the y-coordinate of 2 to the y-coordinate of 5. And in this case, we can see that the right function is now this square root of y minus 1. And we'll subtract out the actual left function that exists now. We know that y is equal to 3 plus x, so y minus 3 is equal to x. The integral of the square root of y minus 1 would be 2/3 times y minus 1 to the 3 over 2 power between 1 and 2. And the second integral, I would have 2/3 times y minus 1 to the 3 over 2 minus 1/2 y squared plus 3y. And this moves between 2 and 5. Evaluating this, we would get 4.5 once again.